Okay. I worked on the program that I shared with you, and it was the bug was the one that I expected. It took like 5 to 10 minutes to figure it out. It was the mixing up of I and J indices in on our image, and also the I and J really is. If you look at this slide that we use to compute our rates, if you see that the value of I does not actually indicate which row you are in. Conventionally, when you have an ij in a matrix, I indicates the row you're in and j indicates the column you're in. But as you see on this figure, it's not like that, because we use I to say, for example, if you look at what I is, we use I to compute SU, which tells you your horizontal direction on the x-axis. So I actually, it's like the columns and the rows of this matrix-like image is reversed. So you should always treat I as your column value or your x-coordinate, and j as the row value. So that was the cause of our error. And when I corrected that, I also solved the first spheres. I'm going to show you that. We also had a bug in the right ppm due to this. When after I change the way I create my image, my array, taking into account the reversal of I and j values, I indicating columns and j indicating rows. For example, let's write the pixel values. Let me comment this out as well. So when we compute our pixel, I didn't change the generate function. The generate function still takes the I and j as they are, but as you can see, the I values here are from 0 to nx, where nx is 0 to 2000, and they actually are the columns, okay, and j is the row value, but the way I'm going to be using them is the way I create the array. I also changed that. I'm going to show that to you. But after I compile, I just wanted to show you the output of this ray tracer. Let's see. Okay. So I also use the square root function, and I also inserted the intersect sphere function to the code. I'm going to show that to you. It was just an implementation of what we have on the slide. Exactly, I converted that to C code basically. So if I run this on our scene.txt, you're going to see that we get exactly the expected result, where our z coordinates do not change. They're always at 13. If you look at your scene.txt file, you see that we had the I was at 5015, and it was 2 units away from us in the gaze direction. So gaze was 00 minus 1. So, and 2 units away, the distance of the image window was 2 units away. So the entire image window should be parallel to the XY plane because of our gaze. If I change this gaze to something else, it will be totally different, okay? It may be, I mean, we may have an image window which is not parallel to any of the major planes. That's totally fine. Actually, I'll show you how we can do that too. But we need to do, we need to compute our u, v, and w vectors by using cross products, not just hard coding their values in them. Right now, in the way we set it up, this u, for example, is to the right directly, saying that our image window is actually parallel to the XY plane. So it shouldn't, we shouldn't just hard code it like this. We should just compute the u vector by cross-producting v with w, right? And w is the inverse of the gaze vector, so it's actually computed correctly like this. And v is read from the input, and this is how we need to compute u by a cross product. But the pixel coordinates looked correct after this. I can actually check the top left pixel coordinate by, for example, going to the top, or maybe I can just put this to output.txt to get all the pixel coordinates. it finishes really quickly. So when you look at output.txt, as you can see, this is your first pixel coordinate. It's 1 and 2, it's closer to 1 and closer to 2. And if you see why is that so, our x-coordinate of the camera was at 5, but the width of the image window was from -4 to 4. Okay, so you need to go 4 units from 5 to the left to get to the left boundary of the image window. So let me get back to, if this is confusing, just let me know. So the x coordinate, yes.
Look, I see that the z coordinate doesn't change, but why y coordinate doesn't change here?
Oh, because we are currently at the first row. We are generating the rays in the
Okay.
first row.
Just
Okay,
first
so
row.
it is going to change. So if we go, for example, to the bottom, so if we go to the bottom, as you can see, the y coordinate changes actually from 2 to -2. So our y coordinate, the y coordinate of the eye was at 0. And if you remember, the bottom and top boundaries were from -2 to 2. So as you can see, the y coordinates actually changed from -2 to 2. But since we are looking at the center of the pixel, it's not exactly 2. Because half pixel width here corresponds to 0.02. So 2 in 1,000 is our half pixel width. Our pixel width and height, they are both equal to each other because aspect ratios are the same. It's actually 0.004. So why is it 0.004? Because, for example, if you divide 8 by 2,000, or if you divide 4 by 1,000, you get exactly, both of them are equal to each other, you get exactly 0.04, which is equal to your pixel width and also pixel height. And the half of this value is 0.02, so therefore it makes sense to start at 1.002 because the x-coordinate of the camera was at 5. So if you go 4 units to the left of 5, you end up at 1. So these look perfectly correct to me as they are parallel. And as you can see, the y-coordinate does not change because currently we are in the first row. If you go to line 2000, line 2001 is the place where you should see the change. So this is line 2000, and this is exactly line 2001, as you see on the bottom right here. And it moves it decreases 0.04 units down, which was our pixel height, right? So they look, and as you can see, the second row starts exactly at, again, the same number, 1.002. So the pixel coordinates look perfectly okay to me. This is the first thing I did was after I corrected this bug, I verified this is the correct thing. But actually I missed out another bug in my write ppm. When we were writing the ppm, so let's see, let's start from which parts I corrected. I corrected, I think, this one. The image, maybe it was first, so first I allocate this many columns, since I'm going to be using the first index to indicate the column of the matrix. Okay, so I arrange my matrix in such a way that the first index indicate actual first index, which is the I coordinate. I will be using I as the first index of the matrix, but that I is going to indicate the column. So I create nx columns, and for each of those columns I create ny length rows, integers. So this is the allocation for a single and y values is the number for a single column. So these are for each column I create this many rows as integers, and this part I change a little bit. But now what I have is I refer to everything as image ij again, but I actually indicates the column index and j indicates the row index, and this is how you can. I wrote my for loops. Okay, then the other thing I added was, okay, I have my my pixel correct. I insert this compute color function for my ray. So since the ray is correct now, we generated the ray correctly. This compute color function, let's go to that compute color function. So for each pixel, in other words, for each ray that is passing through the center of the pixel, our next job is to compute the color of the ray. After this ray color is nothing but another vector 3f. It's actually RGB, but we already have a vector 3f for that with XYZ values. So after I compute the ray color, which comes to me as a value between 0 and 1, the ray color, when I compute it, I arrange in my compute color function in such a way that the colors were like reflectance coefficients, which were ranging between 0 and 1. So the RGB colors that I compute are actually floating point values between 0 and 1. And since my PPM image has to have those between 0 and 1 RGB values, they're actually between 0 and 255 in the PPM file. Just before I write them, just before I write this R value, which is between 0 and 1, I multiply it with 255 to scale it to 255, and this is nothing but rounding back, actually. If you add to a number, if you don't add this 0.5, if you just convert a floating point value to an integer, you're basically truncating it. But if you add 0.5 and then truncate it, it's basically establishes a rounding operation. Okay, so what I write here is just converting the values between 0 and 1 to 0 and 255. Yes.
But how do we sure, like, why exactly 0.5?
Because rounding is mathematically defined like that. For example, imagine you have a 9.3, right?
Yes.
Actually, it's not rounding. So it was, no. Actually, so the value, for example, if you have, if you have 9.3, add 5 to that, it's going to be 9.8. Truncated, it's going to be 9, right? But if something is 9.5, it should be rounded up to 10, right?
Okay, I
So
see.
you add 0.5 to 9.5, it becomes 10.0, and it becomes 10. So this is how you can do. So this int conversion to int explicitly, this explicit conversion makes the truncates that real number to an integer. And if we add 0.5 before we add, we basically define. This is a shortcut for rounding. Okay, but it's not so critical. I mean, what happens? I mean, if you see your sphere instead of 255, you get 254. Is it going to, I mean, will you be able to notice this one level difference in color in your sphere? Probably no. So it's not so critical. Okay, if I don't add these, maybe my images will be very slightly darker, but I don't think anybody is going to notice that. So, I mean, instead of 255, the brightest red, you're going to have 254. I mean, no, it doesn't matter that much. Okay, so, but yeah, the entire thing is actually in this compute color function. And if we go to compute color, it's a very short function. Okay, so first of all, we didn't do anything. We haven't read from our scene file. We have processed our scene file up to this point. Now, the next point in our ray tracing application is to have our objects. Okay, we have set up the image plane, we have generated the rays. Now, by the way, I'm recording right here. So the next step is to get the objects, and then we are going to add the light source later. I'm going to do that today, but first let's see the sphere as a constant color. So we need to have our objects. So we need to, the last two lines here on the scene.txt, they define our spheres. This is the center of the sphere, if you remember, the center XYZ coordinate, its radius, and its color. Oh, by the way, this is like a dark blue. Yeah, I wondered why it was so dark in terms of blue. I thought it was cognitively, I perceived blue color as darker, and human perception. Actually, I gave the color a dark blue color, so I just noticed it now. So, and this is bright red. This is the color of the second sphere, which is here. The interesting thing is that it's like when we were given these values, the center of the spheres, their radiuses, radii, and the camera position, we tried to arrange it on GIMP so that the camera actually is looking at towards these spheres, okay? But we just guessed those numbers. But the good thing is that our camera position, our gaze, and the sphere locations were actually not bad. We were able to see both of the spheres. The red sphere only partially. We see it from the top, but we'll see how we can see both of them as whole spheres. But that's it. So we need to have some sphere objects in our program. So this is what I did next. I just added a very simple sphere struct. Okay, I defined a sphere type by using vector 3f as its center, a float radius, and a vector 3f color. So by using this vector 3f is really useful. So this is a sphere. What constitutes a sphere? Two vectors indicating its color and its center and a radius. So as you can see, the material property of the sphere is embedded within the sphere structure. So this part constitutes the geometry. This part constitutes right now the material, its color. And since I have two spheres in my scene, I just again hard-coded the fact that I have two spheres here on my scene. I have a sphere array, and I set this number of spheres to 2. Maybe I can use this variable later to add more spheres to my scene and maybe make this one something variable. So after I edit the spheres, as you can see, I added the code to the main function to read the spheres after I read the camera parameters. So I just added a function read sphere, which reads those 7 values for a sphere from the file and returns a sphere and assign it to this one. So let's see how that read sphere looks like. It's just one line of code, right? So instead of just, I didn't want to just crowd that part main function. Maybe we could have something else later if we have more properties of a sphere, like other material properties. All you need to do is change this function you have here. You just read something from the standard input. Those 7 values, its center, radius, and color are red, and we return this from our function. And we just, right now at this point, I have 2 spheres that I can use in my scene. That's my current world. Okay, I didn't add anything to the other parts at all. Okay, the main function is exactly the same. All I need to do is now compute the color of my ray. So how do I compute the color of my ray? It's like this. For each ray, for a ray here, you need to traverse your entire scene. So go through the entire scene, which you have this many spheres. You intersect your ray, so this R is my ray, input to this function. You intersect your ray with each sphere one by one. You get the intersection point of your ray with the sphere, you get this T. If T is less than the current minimum T that we have, so our goal here is to maintain the closest intersecting object. And when we are maintaining the closest intersecting object, we need to know the position of the closest intersection point, and the position of the closest intersection point, all I need is a single scalar value T, because I have my ray fixed in this function. I don't need the actual 3D coordinates of the intersection point. I can compute that from this T easily by plugging in this T to my ray function. Right now, I'm not interested in that point. I'm just interested in the closest intersecting point. And this T actually, this parameter T along the ray, the ray parameter T along the ray, which shows the parametric line equation in the ray. This is what T is. We are going to see how this intersect sphere returns that. If it's a closer intersection, if the current intersection is closer than the previous intersection, and also if it is greater than or equal to 1. Why do we have this 1? Because if you know that in our ray equation, we construct a ray from I to the pixel coordinate. So when T is equal to 1, we are actually on the image window, on the image plane. So here, with this condition, I say that I want to only see the objects that are in front of the image window. just like here. So if this is the image, if this is the camera, anything in front of this image window. So if something is less than 2 distance to the camera, if something is in front of the camera but behind the image plane, I'm going to assume that I don't see that. But you can also, if you want, you can relax this one and say that, t is greater than 0. I mean, if you think that objects may come through to the place where between the image window and the eye, if you want to be able to see those images that are there, you may have this change this restriction to t is greater than or equal to 0. But it should be a positive value, because if it's a negative, it means that the object is behind us. We don't want to see it. Okay, and also I'm going to be using the special value of t is equal to -1 as a way to indicate that there is no intersection. So this intersect sphere is always going to return some t. Maybe it's more. It may be more realistic. I don't know. Yeah, actually, what I mean, maybe it corresponds. I don't know whether it's more realistic. I mean, can you see something with between your retina and your lens? It's like something like that. I mean, something inside your eye. I think I would imagine the whole camera system comes with the image plane and the focal point behind. That's the entire camera with that image plane. This pyramid-looking thing is your camera. It's like when t is between 0 and 1, it's like something is inside the camera. But I mean, it depends on how you view it. Yeah, I mean, yeah, you can say t is greater than 0. That's perfectly fine. Yeah, let's do that. Okay, but I think in the assignment we will just ask you to have greater than or equal to 1. Actually, it's like our focal point is in the eye. Actually, the light rays are reversed. The focal point here, exactly, the lens is the focal point. So yeah, you're right. It's greater than physically. What we are doing is we are taking the retina. So when we are making this new model in which the image window is not behind but in front, it's like taking your retina and putting it in front, but just to make your view look realistic. But you're right, actually the lens is the focal point here. So yeah, greater than 0 I think is maybe more realistic. Okay, so if these conditions are met, so which means that if t, as I said, I'm going to be using the special value of t as of -1 to indicate that there is no intersection. So if there is an intersection in front of the focal point, and if that intersection is less than the closest intersection we had up to now, it means that our camera, our ray, should see this sphere. So what I do is I set the current color, I mean the color that the ray sees, to the spheres, to that sphere's color, and update the minimum intersection point. So that's all I need to do. Okay, so that's the entire ray tracing code. Just do intersect your ray with all of the objects in your scene. Keep track of the closest intersection, and store some information about that closest intersection, like the color of the object that it belongs to. Sometimes, for example, if we need other material properties other than just the color, we may just return, for example, it's intersecting with a sphere. Sometimes we may need to know whether the intersection is with a sphere or a triangle, because based on that, I may be using different formulas to compute the surface normal. The surface normal of a point on a triangle and on a sphere are going to be computed by using different equations. So after you identify a closest intersection, what I write here can be replaced with any material property, type of the object you are intersecting, other material properties of the object. Well, I think in my ray tracing implementation, which had these triangles and spheres, I just said that, for example, this is a triangle that I'm intersecting with. I just indicated whether it's a triangle or sphere, and I return the ID of that sphere. For example, instead of tracking the entire color, if I just say that I'm intersecting with a sphere, and the ID of the sphere that I'm intersecting is I, if you just return the index of the object and the type of the object, you can access any information from your struct of your sphere. You have all the material properties about that. Okay, that's more reasonable to do that. Now, the final remaining thing that is in this code is this intersect sphere code, which is just the code to that gets a ray equation, and that gets a sphere, and computes this t, the closest intersection. But if you remember, actually the t has two roots. I mean, there are two t's that are, if our ray intersects with a sphere like this, there are two t's that the intersection occurs, right? There's this t. Can I change the width of this line? I should be, right? Well, what about this? My pen, properties of this pen, pencil. I don't know, maybe, yeah, pencil is better. So this t here, there are two t's, t1 and t2, let's call them. If my ray intersects with the sphere, there will be two t's where the equation, the intersection, when we set that equation to 0, there will be two roots of that equation. And as you can see, we're interested in the smaller one of those. If there are two t's, the smaller one of those t's is the one, is the intersection that I'm interested in. But what if, for example, if your camera happens to be inside this, if you send the smaller intersection this time, this is the one actually in front of the camera, but should you be able to see your sphere from inside? Should you allow your camera to go inside? So just, for example, in the assignment, you are not going to have to deal with such things. All the objects are going to be strictly in front of the image window. Okay, there won't be any object actually between even the focal point and the image window. So it would not matter whether you have that condition set t is equal to greater than 0 or greater than 1, it would not matter. So we are going to give you scenes in such a way that the eye point, the camera, is always behind the objects. So in this case, when our intersection has two roots, we are interested in the smaller of these two. All right. So let's take a look at this intersect function. It seems like a very long function. So this is the intersect ray function. I have these ABC constants set up for my quadratic equation. This delta is the b squared minus 4ac of that quadratic equations. How to solve that quadratic equation. So as you can see, after I compute what ABCs are, delta is simply b squared minus 4ac. If delta is less than 0, it means that there are no real roots of this equation, which means that your ray does not intersect the sphere. So if delta is less than 0, it means there's no intersection, return -1. So this is the special t value that I'm saying. So whether it just means that it is something behind or there's no intersection has the same semantic meaning for ourselves, for us. So if there's no intersection, you're returning -1. So if you look at what these ABCs are, yes.
Hocam, for example, can we use classes with
Sure. Perfect.
instead of
Exactly.
struct and
Yes.
use operation overloading
Exactly.
stuff?
That will be perfect. Actually, you should do it like this. I mean, and more. These are, as you can see, an object-oriented design suits this ray tracing algorithm very well. You have objects, spheres, rays. It will be perfect to have your objects defined as. I mean, you have to have classes for them instead of structs. That would make more sense. Exactly, and you can have, for example, as your sphere may have a method in itself, say intersect with ray, for example. You can directly call that function of your object to see whether that it intersects. You just give the single ray to the parameter of your sphere object, and it will compute that. So that's actually a better way to code this. Then it's more extendable. You can change the object properties. It's a better way to design the ray tracing code. Okay, so as I said, this is the quick and dirty way of doing that, doing it in pure C. Okay, so yeah, if you look at these equations look complicated, but they're actually nothing more than this. Okay, so here a t square. So if you look at what we have in t square here, this is the coefficient of t squared. It's the dot product of the direction vector. So if that's what A is. So if you look at what A is, the dot product of some vector with itself, it's this. So my raised D value, it's the same D here in this equation. That's what A is. So this is the dot product of the vector with itself. This is what A is, as you can see. If you look at what B is 2D dot product O minus C. By the way, this D is a vector, so it has dx, dy, dz component. Okay, so as you can see, 2 times dx, 2 times dy, 2 times dz, and the dot product of that with O minus C. Exactly, I directly, whatever I have on the slide, it's the exact translation of that to the C language, and in converting those vectors to scalar values by taking into account x, y, z values. Since these are dot products, this dot here refers to the dot product, so the result of this entire thing in front of t is a scalar. Okay, so I have a scalar here. And this final thing, which is the c value minus r squared, is the dot product of O minus c. So O minus OX minus CX times OX minus CX. As you can see, OX minus CX, OX minus CX plus the OY minus. So the first thing is I compute the dot product of this. So this plus comes from the dot product of the individual components. And at the end, I should have minus r squared, which is the, this, as you can see, minus s dot radius, s dot radius. So this is exactly, this ABC is what I have here. I got these equations from this single line, and I converted them to this expression, C expression. And after that, after you have ABC, the rest is easy. All you need to do is compute delta. If it is less than 0, there's no intersection, return -1. If it is 0, what does it mean? There's only one root. Geometrically, what does it mean to have delta is equal to 0? How does your ray and what? Exactly, they are tangent. So I couldn't do it. So I should start from here. So your line is actually tangent to your sphere. So there is a single point of intersection. That's what it means. So if that's the case, if it's tangent, we also just return that single root here, which is given by this equation. Otherwise, there are two roots. We take the square root of delta. This is 2a plus, so minus b plus minus square root of delta divided by a. So this is again from mathematics, simple mathematics, the roots of a quadratic equation. We compute these two t1 and t2. Just because we have this plus minus, oh, so this is minus. Is it possible that it's smaller? I think it's always depending on what b is. They may both be negative, but still in that case, t2 will be the smaller one, right? Can we say that t2 is always smaller than t1? Basically, if you see my code, I didn't even bother with that to discuss which one of these t1 or t2 is smaller by just looking analytically to these two equations. I just say that if t1 is less than t2, the thing that we return from the function is t1, otherwise we return t2 from this function, and that's it. That's our ray tracing, first attempt to ray tracing. And when I ran this code, this is the image I got. Let me show you that. Oops, it doesn't look right? I should have two spheres. What is wrong with this? And I was really, actually, I still don't know the reason for this image, why this is green. I don't have any green spheres, and it's like the image is like split in the middle. oh, then I just remembered the right ppm function we had previously had this rows and I didn't update it after this ij mix-up correction of the ij mix-up. So the last thing after I got this image, I went ahead and corrected. I looked at my right ppm function. Where is it? Right ppm. It's right here. So the I and j's were mixed again here in right ppm. So i's the first index I still is the column. So it's from 0 to nx, j is from 0 to ny. So I corrected this one. And after that, I was able to get this image. This is our first image from our, so it's in ppm. So how do you convert it to PNG? I'm going to show you that. And we will actually, I will write into our, I will embed the code to convert it to PNG in our, so right now, wow, it's black because we just ran the code without, by commenting these parts out. So I need to run it again like this. Let me save it. Okay, now I'm going to compile and run it. So this is the output PNG. So let's see how our first spheres are going to look like. So let me, I compiled it. Now I run it. Now let's take a look at output ppm. Okay, so this is our first image, two spheres. The red one is not entirely visible from where we are seeing. And as you can see, it's actually doesn't look like a perfect disk. It's like distorted, right? Because of the perspective vision. This is closer to our camera, and that's why the perspective distortion, the far away objects look smaller, right? So the far end of the sphere, actually, the perspective effect is so visible because this object is much closer to us, okay? And this one looks more like a disk, and it's actually darker. So let's make it a lighter color. Oh, I just closed GIMP entirely. Let me open that again. File, new, that's my whiteboard. And resize. Okay, now if we have the pure blue, let's modify our scene. If I make the blue 1.0, okay, and I don't need to recompile it, it was just the input. Okay, so let's take a look at it again. And looking at the GIMP all the time, these ppms actually, as you can see, it may be annoying to just, so it's actually now lighter. Now, why did I answer? So you asked, Yusuf, why is it distorted? Because of perspective vision. In perspective vision, close away objects appear larger than far away objects, right? And the back end of the sphere is actually far away from us than the front end. So in real life, you don't, all the objects that we actually perceive around us. So why don't we see objects this distorted in real life? You may say, because this perspective effect is not so, the difference between objects, when you view a sphere, you view it like this, and the difference between, you put it in front of you like this, and the difference between those are not that drastic compared to the distances we have here. So the perspective is more pronounced here for this sphere, and as you can see, this doesn't look that distorted. So this is due to the perspective. For example, if we had a cube, a perfect cube, and if you were to look at from very close the cube, it will actually, the back end of the cube is going to look smaller than the front end, right? If imagine you have a cube in front of you, the front side of the cube is closer to you than the back side, and therefore the back side of the cube is going to be smaller due to perspective. And depending on different camera settings, and this perspective effect really depends on your field of view, your camera settings, how far your image plane is, from image window is from the focal point. So all these things, your field of view angles, they affect the amount of distortion you're going to have. So yeah, these are our first spheres, but I mean, we just wrote like 200 lines of code just to draw these dull-looking spheres, right? And you're going to see why, with simple additions, they will look fantastic. So in 10 minutes, maybe, I'll be able to do something that they will look. In the remaining 10 minutes, we may just implement the diffuse part of the shading part, which will give them some kind of a nice shade. But for that, we need to have a light source. I can just right now hard code the light source in my code. Let's see. All right, and I want to show you some quick thing. There is a function by ImageMagick. Right now, my ImageMagick is not installed on my Ubuntu here, but let me try to install ImageMagick quickly. Let's see whether it's going. It should be quick. Yes, 80 megabytes. So it comes with lots of utilities. Okay, so it's actually a really good tool. I recommend you to install ImageMagick for image processing related stuff. It converts images to other. It has this convert utility which can convert between different image formats, and this is what I plan to use. All right, so. It's taking longer than I expected. It requires lots of other. As you can see, it installs a lot of libraries, but it's about to finish. Yes, waiting for the last post-processing jobs. It's doing. Yeah, it's done. Now, when you say convert output.ppm, output. I already have output PNG, I guess. Output 2.png. Now, as you can see, it does it in an instant, and I have in my file here output.png. Now you can see your images in your most favorite photo viewer, whatever it is. And another big effect of this is look at this, the size of the file. A 12 megabyte ppm file can be compressed to, because our scene just contains lots of black color and just constant color, it's just 5 kilobytes. Okay, so 12 megabyte, 5 kilobytes, a huge space saving. So what I'm going to do is I'm going to actually write here in my right image here, where when I have this, where is my right image? I open output.ppm. At the end of this, I'm going to make a system call. Is it the system call or exec call? Was it like this? Yeah, there's the system calls like this. Convert. It's just going to be again hard coded. You can get file name information from the user if you want. Output.png. And after that, I can even delete. So let's also remove. My insert is on, yeah. Remove output.ppm. So let's see. So I don't need the ppm version at all. So let's compile this and run it quickly. And I still have 5 minutes to do the shading. Where do I, yeah, compile, run. Image data output ppm. Oh, maybe I need to wait for a while? No, it should be. Oh, where did I put it? Let's see. Convert output ppm. It was output ppm, right? Maybe the system file is looking at a different directory. Maybe the case. Anyway, you can figure this out later. I don't want to spend time on this, but you can just. I will do the conversion later after I do that here. So let's compile it and run it again. So whenever I run this, I think the reason was, I think it's open in GIMP and it was unable to write on top of it. That's why it was correct before. Yeah, it wasn't able to open it for writing. I think that was the reason. No. Is it still open here? No. Output ppm, or is output ppm open elsewhere? I'm not sure. Yeah, so I'm going to do it here. Convert output ppm, output png. After I run it, I have this 2 lines that I have here, output.ppm. Now, my output png is now correct. Now, well, how can we make these 3D? Now, I'm going to write here, first I want to detail what I'm going to be doing, all right, on GIMP. So here is what we have. We know our ray intersects with the sphere at some point t. And what I'm going to do is, I know the point location. If there's a light source here, I'm going to, whatever color I'm returning, I'm going to scale that color with the dot product of the normal vector here and the light vector here. Okay, let's call this light vector. This is the normal of the surface. Let's see what is the normal of a surface at this intersection point. It's simply whatever this intersection point is, this minus the center. Let's call this intersection point P. P minus C normalized, the normal version of this P minus C vector is my normal vector. And my light vector is simply wherever the light is located. Let's let this light be located at L. If I do L minus P and normalize it, this vector is the light vector, okay? Now, what I claim is that the dot product of these two normalized vectors, if I take the dot product of these two, and if you, whatever color you have, for example, if you have your red color, if you multiply your red color, if you scale your red color with the dot product of these two vectors, your image is going to have what we call the diffuse component. So this, the thing that I compute here, the dot product between the normal vector and the L, we are going to see in the shading slides next week that it's actually how diffuse color is computed. So let's do that, okay? Quickly, actually I will spend maybe 5 minutes more of your time because I need to have this normalize the vector type of thing. I need to implement it. I need to insert the normalize function as well. Dot product is easy to do, but let's have our light. Okay, vector 3f. Where should we put the light? For example, somewhere, let's call it light. And so light dot x is, for example, if we put the light at the top, 0 and somewhere above, for example 0, 50 and 0, x, y, z. Okay, so we put a light source at the ceiling at a high location, just on the y-axis. This is my light location, and let's make this a global variable here, because I will be referring to that in my compute color function. So this is my light. Okay, now where's the compute color? Right here. Now, after we have this, instead of returning C, this is what I'm going to do. I'm going to have two vectors, the Ln vec3f L and N vectors. L is simply, the light vector will be simply the addition of the light location and multiplication of S with -1 and the pixel, the location of the pixel. of the intersection point. Where is the location of the intersection point? It's actually the my ray's origin. Okay, the ray had this origin. If I add this to this multiply as ray's direction, which if I multiply this min t, the intersection point, minimum t is my intersection point. If I multiply this min t with d and add to that my, so look at this part. What does this give you? Addition of origin of the ray, min t times d. So this is that point P. Actually, I can do that here. Let's call it vector f P. Let's first compute P. The intersection point is given along the ray by just plugging your, this is basically plugging in min t to your ray equation. This is my point P. And if I compute L minus P is my light vector, okay? And my normal vector will simply be P minus the center of the sphere. So to get that minus spheres, now which sphere is it intersecting with? As you can see, I need to get the sphere ID here to show the color is just not enough. Maybe let me just say here min I is equal to -1 and integer min I. Okay, so I'm also keeping track of the intersecting sphere, which sphere it was intersecting with, because I need to get the center of the sphere to compute the normal vector correctly. So this L and N vectors are now my light and the normal of the surface at that intersection point. So why is it that the normal vector? As you can see, if you have a sphere like this, the normal of a point on the surface of any sphere is this vector from that point to the center. So the normal vectors goes like this, right? So therefore, the normal of any point on the sphere is whatever that point is. This vector, which is P minus C, is your normal vector. Now, the final thing that remains is what I'm going to do is see, and I need to do all these things if min I is not equal to -1. Okay, because otherwise I need to return the background color. There is no intersection. Min I is going to be equal to -1 when my ray intersects with no spheres. Then in that case I should return the background color, which is given as 0, 0, 0 here. Okay, so if there is intersection, it means that min I is not equal to -1. I compute my P, L, N values. Now, all I need to do is, maybe I can leave this so that you see how the spheres are going to look like yourself, not here on your own machine. Now, the only thing that's left is L is equal to normalize L. Actually, I can do that quickly right now. So, and N is equal to normalize N and return. So actually, C is equal to my color is going to be, I'm going to scale my color this time with dot product of L with N, and that's it. Return C. So, okay, so this thing, all the only remaining functions are normalizing a vector and dot product between two vectors. Let me quickly write those. Vec3f, first write the easier one, Vec3f AB, let's call them AB, Vec3f B. Return a dot x times b dot x plus a dot b, b dot a dot, sorry, y, and z. So that's the dot product. We did the dot product. Let's do the normalize. Vec 3f normalize any vector vec3f a. So let's compute the length of the vector. Oh, the good thing is the length of a vector is it's the dot product with itself, right? So all I need to do is return square root of the dot product AA, right? This is the, is it correct? Is there anybody here? So let me see whether you're still on on WebEx or not. So where's my WebEx? So how many participants are there? There's 20 of you are still here. So I think this gives the, so this is the length of the vector. So what I need to do is I need to multiply s, the length of the vector, 1 over the length of the vector, 1.0. I need to scale my vector with this. Now it's normalized, right? Is it so? As you can see, this is like the this one, the dot product, and sorry, the dot product AA square root now square root parentheses is correct. So 1 over square root of the dot product of the vector itself is the length of the vector. So in order to normalize a vector, I need to divide all of its components by the length. So this 1 over thing gets that division factor. And yeah, let's see what it turns out. And it's actually, we're done. And the only thing, the order of the parameter, is it the scaling, this mults? So how does mult s work? Let's see. Wow, it's all my mult s's. Actually, you're right. It's actually the vector first. Okay, so the vector first and the scale. So I use it in a couple of places incorrectly. So I need to change that, and then it will then be correct. So this is multi-s, compute color, read sphere, intersect. Yeah, here it should be A than the other one. So you need to, yeah, it's also, as you can see, this is one of the disadvantages of not writing my code in an object-oriented manner. All my functions are static, so I need to keep track of the order of parameters while I'm coding them. So there was, here we also had the same thing, right? -1 actually should come later. -1 here, also p -1. All those things, D should come. No, this was correct. No, the vector should come first, and it's actually r dot d, not just d, and then min t. Okay, the vector comes first, x -1. Okay, and the final thing is see this. Now, what I want to do is, if the dot product of this ln, if it's actually less than 0, I should just return. In that case, it should be black color, okay? But let's just leave it like this. I don't want to get different effects. So, but only if the dot product is greater than 0, we'll be able to see something. But if I don't add this, let's see what happens. There may still be some small bugs, but we'll see. Let's run it, and then I'm going to finish today's lecture. Oh, no, multis. Yeah, there's another one here where we compute the color. So C is the vector. Yeah. The vector should come first, right? Yeah. Here. -1 like this. Was there any other place where I used it incorrectly? It seems I got lots of errors there. Let's see. Spheres min I. Oh, it's the center. So we need to get the center of the spheres. Spheres min I dot C. So my sphere struct has the C as the center coordinate. Okay, so I need to get this one. That's another thing. But yeah, I don't want to spend more of your time. I'm going to just, the code is almost complete. I'm going to share this code with you. Okay, online, the parentheses is wrong. Yeah, here, mult as, oh yeah, you're right. We need to have this one here and here, like this. Actually, it was missing one parentheses, but let's see. Yeah, I'm going to actually just want to show you. If you don't have, if you have other classes, you have to go. Please, I don't want to keep you waiting, but I just want to show you this by getting rid of these errors. This mult as, here we also have this in line 188. I need to also figure this out. So here, the dot product, C is the color, right? It's the vec3f, so it should be correct. What am I doing wrong here? C is the color, it's the vec3f. So we write the vec3f first in mult s. So it should be, so the dot product, the result of the dot product is a scalar. Oh, am I returning? Yeah, it should be scalar. So it's just, it should be just a float. Yeah, most of the errors are probably from those. And my sphere has, I think it's named center, not C. So the sphere center, spheres that center, that's another error that we need to fix. And another parenthesis in line, only two errors, 155 and 184, they're just parentheses mismatches. 155 here, the square root, and then, so it's first the dot product, then the square root of that, and yeah, there was one more parentheses not needed, and 184 here, the final thing, mult is this one. This is multiplication, this is addition, and yeah, there were excess parentheses at the end. Now, let's see. Yeah, it's compiled finally. Let's run it on our scene, and let's convert our output ppm to PNG, and let's see that output PNG. Oops. Some bugs in our, probably maybe the normalization, but we get some interesting 3D spheres, but a really strange bug here. Look at this. It looks nice actually. It's like if you zoom in on this, wow. I mean, but this is the effect we were hoping for. Okay, now our spheres should look like like this. I mean, the top of the sphere looks perfectly fine. But I think there's something wrong with our, where's the red sphere? What, look at these different colors. It's a really strange effect that we're having here. So I leave the solving this by probably our normalized function, or maybe the length of the vector. I use dot product for that. It may have been wrong, but it should be correct. I'm not sure. So I'm going to share this final code with you, and I leave the having both resolving the bug to you until next Tuesday. Okay, so that's it for today. Have a good weekend, everyone. Sorry for taking 15 minutes more of your time, and I will stop recording